So this is a silly little video just to kind of get you started thinking about friction and systems and stuff like that. Just different ways that you can have these friction-y thingies set up. So like if we have friction on wedges, I guess is one that we'll look at. Like let's say we've got, can't decide how much to draw this. Like this, like a little, I guess a wall or something. And we've got this little like weight here with this funny little angle, and then this like wedge here. Okay, well, we'll just pretend that they're touching. I guess I could just make them touch and that would be okay too. So, and I guess it's supposed to be lined up better. I can't do this. Okay, that took way too long to get looking the way I wanted it to. Okay, and this is empty space for the purposes of space, empty space. So, this is not a great picture, and it's not a thing that ever happens particularly in real life. It's just one of those things that like helps us talk about some things, I guess. So like assuming you had some kind of a weight here, and it's funny because a lot of times things will end up being weightless. So let's have something that does have a weight and like a weightless wedge here. Okay. So the question is like, how do these interact with friction? So whenever you're trying to draw these and draw the, the free body diagrams, it helps to break them apart for sure. So let's pretend that there's like, a little thing, and maybe picture that as like, your foot pushing the little wedge beneath the door. But this is kind of weird because this would be the idea that you would have to kind of keep your foot there to keep the door from closing. If I took this off, then once I wedge the wedge under the door with my foot, then it would stay there. So for the moment, let's just put that on there, assuming it's a bad wedge and you're trying to hold the stupid door open, so you've got your foot under there. And again, I know the bottom of the door doesn't look like that. We're just playing, okay? Okay. So let's break these apart. So first of all, we've got this little wedgy thing here, like that's actually not technically supposed to be the wedge. That's just the general weight. All right. So look at that dude. W, whatever it is, W. Okay. And then we've got this piece here. And it's entirely possible that you're looking at this going, I've never had a problem with this picture. I don't know what's wrong with you, but I can't picture stuff. And so I have to like really, really kind of think super hard about it. So if I'm looking at the system, okay, I could say like, okay, so on the system, there's some kind of a normal force here because it's touching. And then there's some kind of a normal force here, normal 1, normal 2. And I know there's some kind of friction, but I can't decide which way it, that's not supposed to be squared, that's supposed to be a question mark. I can't decide which way it's going. And I guess this one I could probably be pretty happy with the idea that this friction is going this way, just because I can look at this force and be like, oh, okay, well, if I'm pushing it in, then clearly it's trying to come back out. So I can say that this is opposing the motion of getting schnooked into the thing. So I can redraw these external, what used to be external forces. Well, they're still external, but we now have exposed some internal forces. And so the question becomes, where do I put that stupid frictional force up on the top right? So I've got the normal and I've got the weight. Okay, so I've kind of met the requirement of whatever was external before. 1, 2, 3, 4, 5, 6. I still have 1, 2, 3, 4, 5, and 6, even though I don't know what direction that stupid friction-y thingy goes. And then I've exposed the internal forces, what had been internal forces. And that actually helps me figure out what I'm doing. And so let's see, we've got a normal force that these two have to each other. And we draw those so that they cancel out. We have to name them the same thing, N3, equal in magnitude and opposite in direction. Okay, and then as I kind of think about what's going on, it wouldn't make any sense that if I was going this way, that this friction would be going this way and that friction would be going that way. Okay, does that kind of make sense? So it makes sense that the frictions are going the same direction. And so by breaking it apart, I'm able to kind of argue my way through this a little bit better. So I'm going to put this frictional force has to be opposing the motion this direction, which means that this frictional force would need to be opposing, I'm really supposed to draw it on the inside, but it's so you can see it better, but I'll put it where it's supposed to go. Shudderp, shudderp, shudderp. So this frictional force has to go like right here. And again, it's kind of the same thing, that if that's going that way, it doesn't really make any sense for this frictional force to be going this way. Like I can't figure out a way in which it was moving up, and like if the motion, the only way that this particular picture would work is if the wedge or this force up here was trying to move this way and this way at the same time. And clearly that's not what it's doing. So we are kind of committed to having this dude, I can't draw an arrow now because coffee. We are kind of committed to having this one face this direction because remember that opposes motion, so it's trying to go up. So since that one's trying to go up, then it only makes sense that this side is also trying to go up, which means that this friction force has to be facing this direction. And so along those lines, I can come back over here to my original and I'm like, oh, that's supposed to be 1. I can go back here to my original and be like, okay, so clearly that is facing this direction. And then I look super smart, like I just knew that all along. But breaking it apart just helped me kind of picture it. And so this is just one of my little brain things, like what do they call it? Mental gymnastics that I have to do to draw these effectively. And some students are just like really good at being like, this goes in, so clearly this is trying to go up. But then like I'm going to argue with myself of like, well, it's actually trying to go down because it's a weight and it's trying to go down, and so stuff like that. So breaking it apart helps. And oh, I think I mentioned this earlier, but just in case, if this force isn't there and it stays in place anyway, it's called self-locking. If there's no, let's say with no P. So if there's no force holding that wedge in place, it's called a self-locking wedge, or you have like self-locking screws, self-locking whatevers, which means that whatever coefficient of static friction is going on between these two buddies here and this buddy, and I guess really all of these, that it's just, they're all super happy and they're perfectly content to hang out in place without the extra force here holding it in, and that's called a self-locking wedge. But anyway, oopsies. Doing stuff like this, just, I guess the whole point is sometimes breaking things apart makes them a little bit easier to kind of argue your way through and kind of understand what's going on.